Hello friends, in this video we are going to discuss about the generation and recombination in ambipolar transport. From ambipolar transport, know that this type of transport happens or occurs inside the semiconductors when there will be a generation of excess carriers inside the semiconductor, both for intrinsic and extrinsic semiconductor. And we also know that the electron recombination rate, that is the electron recombination rate, is equals to Rn. That is, if we denote Rn as the electron recombination rate and Rp as the whole recombination rate, then we know that from semiconductors that the recombination rate of the electron, that is Rn, will be equals to Rp. So we can say that the Rn is equals to Rp, and we know that the Rn value is equals to the electron concentration, that is N, divided by tau of Nt is equals to P by tau of Pt, where this tau of Nt and tau of Pt defines that tau of Nt is equals to mean lifetime of the electron, and tau of Pt is equals to mean lifetime of holes. We have already seen this thing in the previous lecture. Now, if we have a p-type semiconductor, so let us take a p-type semiconductor. So in this p-type semiconductor, under low level injection, we say under low level injection of excess carrier, we have seen that what we mean by the low level injection. Low level injection means that the excess electron concentration in the p-type semiconductor, that is del N, will be very much less than the majority carrier concentration P0, that is the whole concentration in the p-type. This means the low level injection. So for excess carrier generation condition, and if the under low level injection is happening, the concentration of, we can write that the concentration of majority carrier, and we are taking the p-type semiconductor, so the majority carrier will be whole. So the concentration of the majority carriers will be constant during the excess carrier generation, but the concentration of minority carrier, that is the electron, will increase by several order of magnitude. This is the thing that we have seen earlier in the previous lectures. So we can see that the majority carrier concentration is not changing, but the minority carrier concentration is increasing by a several magnitude. That's why we can say that is therefore the probability of, that is the probability per unit time of a majority carrier encountering an minority carrier will change drastically because the minority carrier concentration is increasing by an several magnitude. So encountering of majority carrier with the minority carrier will increase drastically, and the time or the probability per unit time will increase in this case, and these physical phenomena or the probability per unit time can be denoted by 1 by tau pt, where tau pt is nothing but the mean lifetime of the holes. So we can say that 1 by tau of nt will be the probability per unit time of a minority carrier, and in this case the minority carrier is electron because we are considering p-type semiconductor encountering a majority carrier, that is the holes for this case will be constant because the majority carrier concentration is not changing drastically. Only the minority carrier changes concentration drastically. Similarly, so this happens for the p-type semiconductor. Now, if we consider the n-type semiconductor, so for we can write that for n-type semiconductor, when the excess carriers are generated, when excess carriers will be generated, we can see that the majority carrier, that is the electron lifetime, will change drastically. That happens in the p-type semiconductor also. In the p-type semiconductor, we have seen the majority carrier, that's the whole lifetime, has been changed drastically. And here for the n-type semiconductor, the majority carrier concentration, that is the electron lifetime, will be changed drastically. Similarly, the minority carrier, that is here it will be whole lifetime, will change zero. That means it will remain constant. This is the thing that we can see for the n-type semiconductor and p-type semiconductor when the excess carriers are generated. So if we consider the generation and recombination terms in the ambipolar cases or ambipolar transport, let us consider that small g is the generation of carriers and small r or capital R. Let's take capital R. Capital R is the recombination rate of carriers. If we talk about the electrons, that is for electron, we can write that G minus R, that is the generation rate of the electrons minus the recombination rate of the electrons, that is G minus R, can be denoted as, since we are considering electrons, we will write G suffix n, n is for electron, and R suffix n. So these Gn minus Rn can be written as further Gn0 minus, rather it will be plus, minus Gn dash minus Rn0 plus Rn dash, where this Gn0 denotes the thermal equilibrium electron generation rate, and this small gn dash represent the excess electron generation rate. Similarly, this Rn0 will represent the thermal equilibrium electron recombination rate, and this Rn dash is the excess electron recombination. So if we look at this equation, we can see that there are four terms, and out of these four terms, the two terms is considering the thermal equilibrium condition. So further we can discuss that we know that the Gn0 will also be equals to the Rn0, because the thermal equilibrium electron generation rate will also be equals to the thermal equilibrium recombination rate. So this equation, if we denote this equation as 1, then from the equation 1 we can say that small g minus capital R will be equals to Gn dash minus Rn dash, because Gn0 and Rn0 will be cut down, because Gn0 is equals to Rn0, and this Rn dash further written as del n by tau n, where del n is the excess carrier concentration and tau n is the excess minority carrier lifetime. Similarly, we can write the thing for holes also. For holes, we can say that P minus R, that will be Gp, because we are considering holes. So Gp minus Rp. So Gp can be further written as capital Gp0 plus small gp dash minus Rp0, that is the recombination rate of the holes at the thermal equilibrium, plus Rp dash. Since this Gp0 and Rp0 will be equal, so we can write this equation as Gp dash minus Rp. So further we can say that if we put the value of Rp dash, then it will be del P by tau P. In this way we can find the G minus R for holes and G minus R for electrons in the case of ambipolar transport. And the ambipolar transport equation for low level injection can be written below like this. That is, if we write the ambipolar transport equation for low level injection in, first let us consider the p-type semiconductor. So the equation will look like dn, that is the diffusion coefficient of the electron, del 2 by del n del x square plus mu n into capital E del of del n divided by del x plus g dash minus del n by tau n0 equals to del of del n divided by del t. So this will be the equation for p-type semiconductor for ambipolar transport equation. Similarly, we can write the equation for ambipolar transport in n-type semiconductor also. So if we consider the n-type semiconductor, similarly for n-type semiconductor also we can find the ambipolar transport equation, and it will look like dp del p del 2 by del x square minus mu p into E into del of del P divided by del X plus G dash minus del P by tau P0, that is del of del P divided by del T. This is the equation of the ambipolar transport for the p-type semiconductor, and this equation is the ambipolar transport equation for the n-type semiconductor. There are some derivations also, but derivations is not required for the gate examination. You need to understand these equations only. Okay. So for that case, if I look at the individual terms, then I can say the first term, this first term contributes to the diffusion motion of carrier. If there are some diffusion motions of the carriers, that is the excess carriers, then we will get this term. And this second term will contribute for the drift motion of the carriers in external electric field. Similarly, G dash is the generation rate of excess carriers. Similarly, this one, the fourth term, is the recombination rate of excess carriers, and the right hand side gives the rate of change of excess carrier concentration with time. So the first equation and the second equation describes the diffusion, drift, and recombination of excess carriers, minority carriers, as a function of spatial coordinate as well as the function of time. That means in these two equations you can see that we are describing the diffusion motion of the excess minority carrier, we are describing the drift motion of the excess minority carriers, and also the generation and recombination of excess carriers with respect to the spatial coordinates as well as, that means the distance, as well as the function of time. And the excess minority carrier is changing like this way, following this equation. If we talk about the excess minority carrier, the excess minority carrier will diffuse and drift with this excess concentration. So the behavior of the excess majority carrier can be determined by the behavior of the excess minority carrier parameters, because according to the ambipolar transports, the majority carrier and the minority carrier which has been injected inside the semiconductors, that means the excess majority carrier and the excess minority carrier will diffuse and drift in an altogether fashion, in a combined fashion. So if we know, or if we determine the excess minority carrier parameters for this drift and diffusion motion, then that will also be valid for the excess majority carrier. Now this is the ambipolar transport equation for the low level injection in both p-type and n-type. Now if you do some modification this equation of ambipolar transport with different conditions, that means these two equations will change with respect to the conditions present at the semiconductor. So let us discuss about that condition. So we can write that the modification of the ambipolar transport equation with different conditions. How the above two equations, previous two ambipolar equations, will modify itself when there will be different conditions. If, let us make a column. So in the first column, I am taking, that is, it is the situation that is present and what will be the effect on the ambipolar transport equation. So if there is a steady state condition present, then the term that contains del n d of del n by del t will be 0 in the transport equation. Also, the del of del p by del t will be 0. Steady state means there will be no rate of change excess carrier concentration with respect to time. That's why these two terms will be 0. Similarly, if there is a uniform distribution of excess carriers. If this happens, then there will be no diffusion. So if there is no diffusion, then the first term, that is dn del 2 of del n by del x square will be 0. Also, the dp del 2 del p by d of x square, 0. That is the uniform distribution of the excess carriers. So it is happening for the steady state, and it is happening for the uniform distribution of excess carriers or uniform generation rate. If there is also, now the third situation, take the third situation, if it is zero electric field present, there is zero electric field present, then what will be the modification that can be done in the ambipolar transport equation? That means the term containing the electric field or the drift, that is capital E, del of del n by del x will be 0, and also del of del p divided by del x is equals to 0. So it will be a zero electric field conditions. This will be the modification. Now, if there is no excess carrier generation, then what will happen? So for that case, let us take the fourth situation, that if there is no excess carrier generation. If there is no excess carrier generated, then we can say that the term containing the generation G dashed will be 0 in the equation. So for the fifth case, let us consider if there is no excess carrier recombination happening inside the semiconductor, then at that case del n by tau n0 will be 0, or for the case of excess holes, del n del p by tau p0 is equals to. So in this way we can modify the ambipolar transport equation. This is all about the generation and the recombination in the ambipolar transport phenomena that will happen when the excess carriers are generated inside the semiconductor. Thank you.